Okay, so let's talk about the general design process. We know what the subsystem is responsible for, what the lead needs to do, but in what order do we do all of these actions? So the first step is to gather requirements. We need to gather requirements from the components, such as their thermal sensitivities, and we need to gather requirements from external references. Here, I just have an example of NanoRax's expected thermal environments that the spacecraft needs to survive through storage. And then just an example of a component, what its charge and discharge thermal or operating temperatures are, and also what its storage temperatures are. The next step is to compute maximum and minimum orbit temperatures using surface property estimates, solar flux density, and average power distribution. So this maximum and minimum orbit temperature is likely going to be driven by time in the sun. So let's dig into a concept called beta angles in the context of the ISS orbit. Here is a plot showing the duration of eclipse, so the amount of time that you're out of the sun, given various inclinations and altitudes. So let's take an example where we are interested in inclination around 60 for the ISS. It's more like 50 something, which is going to be around here, but let's just follow the 60-degree path. So the 60-degree path at, let's say, 400 kilometers is going to be like down here. We're going to expect an eclipse of about 30 minutes. I don't know if that's exactly true, but the concept is here where your height and your inclination dictate the duration of your eclipse. And you can see that here, where you can see that in both of these pictures, where the ISS in its inclination will enter eclipse when it crosses this shadow boundary, and it'll be in sunlight otherwise. You can also see it at a different angle in this, more looking down into the orbital plane of where exactly that shadow boundary is, where Earth's shadow is a cylinder. The edge hugs the circumference of the Earth, which is a sphere, and it just gets projected in a line. Okay, yep. Another way to compute maximum and minimum temperature of the spacecraft in its orbit is how much average power is it dissipating. So you have all of these components. They're ingesting electricity, energy, but they're not totally efficient and they dissipate heat. So you need to be attentive to how much energy, heat energy, is the spacecraft shedding while it's operating these different components. And this is a table of the components inside the Artemis CubeSat kit. Okay, so once you have that information, you can calculate the equilibrium temperature of your spacecraft as a system. And you can see if, as a whole, your requirements can be met with just passive thermal control. Passive thermal control is simpler, usually has less mass. You can just apply a surface coating or some radiators and call it good. So I just want to demonstrate conceptually what the equilibrium temperature of different spheres are from ground to space, given different surface coatings. So conceptually, if you take, let's say, a pocket of air from ground to high altitudes, the temperature profile looks like so. If you take a block of material that is covered in a white surface coating, then you are going to, your equilibrium temperature, so the temperature that you would settle into given infinite time, would be around, let's see, it would be the coldest, right? Because white reflects. On ground, it would be really cold. But then as we get up into space, this cooling effect gets more pronounced. If we then look at something like gold, on ground, it would be like room temperature. And then we would see that the steady state would actually be quite hot. And then if we had something that was coated in black paint, then it would start out very hot, and then it would steady state somewhere in between a comfortable, it would steady state to like maybe 10 degrees Celsius. Anyway, the point is surface coatings matter. If you can get away with a passive solution like surface coatings, that's pretty ideal. So what if we want to get more into the details of what your thermal distribution is within the spacecraft? Then you have to develop a multi-node thermal model. Here you'll see different examples of finite element analyses. Here is a spacecraft cut up into a bunch of different elements. Hot components seem to be up here. This is the system as a whole. And then you can take a look at smaller systems, so component level, subsystem level, thermal analyses as well. To create the finite element analysis, or to do an analysis in general, you need to determine the conduction and radiation couplings that will eventually lead to acceptable temperatures. So within your model, there are joints that transfer heat. Down here, I have a picture of how you can do thermal analysis through circuit analysis. So there are different equivalents. You can take heat energy as the energy coming into a certain node with a certain temperature. And I think conduction can be thought as a resistance between two temperature differentials, which can be thought of as electric potential. And that can be radiated off. I think that relationship is capacitance. Anyway, the point of this slide is there is analysis you need to do between the joints of that are dominated by conduction and radiation. These different circuit diagrams can help you visualize all of the flows of heat that are going through a system from end to end. And it can help you predict performance for different scenarios of couplings. So like, what if I cut this, this section off and isolate TE to TC, then how would the heat flow change? And you can get graphs like this that show you if I enter a cooling load over here, then the subsequent analysis shows me that I'm going to get a steady state temperature of about 290. And then there's some, I don't want to get into the last plot. Yeah, okay. And then the next slide is going to make that a little bit more clear, where you can see an actual system. It's CAD. And you can see how this CAD is broken up into some kind of thermal node analysis. You have the resistances across different conduction paths. Ground is where you can just shunt heat energy. But the last step of the general design process is to do a thermal balance test. Part of it is to create a predictive model to see what you think the system is going to do, and then you want to put it into a thermal vacuum chamber to see, does it actually do what I think it's going to do? So here is the telescope LORRI from the New Horizons spacecraft, where here is a thermal model, predictions, and then they took the real system as built and put it within the shroud, did some testing in it, and measured temperatures of different components within this subsystem, just to verify that all of the components not only behaved as expected, but also the physical system, the components stayed within their comfy range.